Okay guys, in this lecture I want to introduce the concept of the electric field and just fields in general. This goes with the reading 2.1.3, and again the learning objective is just to give you guys a conceptual understanding of what is meant by the electric field. Okay, so I wanted to start with these couple of images. This image is the result of this child's hair being subject to an electric field that she feels, or that is the result of her being charged by touching this Van de Graaff generator. Basically, she's getting an excess positive charge on her, and that excess positive charge extends to her hair follicles, and you can actually see them, because they're all positively charged, repelling one another. On this side, we've got iron fillings that are tracing out the three-dimensional magnetic field around the ends of a horseshoe magnet. The reason why I wanted to look at these images is I want you guys to imagine back in the time of Michael Faraday. Michael Faraday is another big-time scientist when we're talking about electromagnetic theory. If you look here, he was born after Coulomb published that paper that I talked about when we were talking about Coulomb's law that described how the electric force fell off like 1 over the distance squared. So this gives you an idea about the progression from experimentalist to theory. Michael Faraday had kind of humble beginnings compared to a lot of our early white male physicists, right? He didn't come from a rich background, but he kind of worked his way slowly into the highest level of physics. And he was not known to be a great mathematician. If you look here in the Wikipedia article, it says his mathematical abilities did not extend as far as trigonometry, and were limited to the simplest algebra. So he wasn't a great mathematician. He probably would have struggled, right, in this course that you guys are taking right now. But he was an excellent experimentalist. He knew how to design experiments and observe phenomena. And through this, he built kind of the conceptual, or our basic understanding, our non-mathematical one, but the actual understanding of what's happening with electromagnetic fields. He is the one that's credited with coming up with this concept of a field to describe what is going on around charged and magnetized objects. And I like this image here because it's actually not that hard to imagine how Michael Faraday might have come up with this concept of a field. In the right kind of situation, right, you can produce ways to visualize what this field might look like, right? This girl's hair is very much, what it's actually doing is very similar to how we might draw the vector force field around this charged object. And same thing here with the iron fillings. They're basically tracing out, what would we draw on a picture of a piece of paper to describe what a magnetic field looked like. So these kinds of experiments, the iron fillings and Van de Graaff type generators, these were not uncommon during Faraday's day. So he was observing this phenomena, and it made sense to him, okay, that this electrical force wasn't something that happened just kind of magically through empty space, but electrical forces happened because the space around these objects was being filled with something like a fluid, which he described to be a field. Okay, so that's what you want to think about with the field. The concept of a field being, right, something that is invisible, right? If we didn't have these tools, we couldn't observe it. But there's clear signs that around these special objects, there is this kind of fluid created that enables these forces to act on objects, okay? So fields are physical objects. They are not magic, okay? It is not just a mathematical construct. The space around you, even if you were in a vacuum, would really be filled with what we'd call an electric field. It is something that we can measure the strength of, the direction of, and in fact it's something that travels with a particular speed. So it doesn't instantaneously fill a space. It fills a space at a very fast speed, but a finite speed nonetheless. Okay, and we also know how fields travel in different mediums. We know that electric fields travel differently in a vacuum than they do in say, a solid object. Okay, so this is something I want you guys to note, is that fields, they're physical, okay? They are physical objects. Okay, they are real. Okay, and we even know how they travel through different mediums. And of course, we now know that the electromagnetic field is actually a wave that transports energy even through a vacuum. Okay. What we're going to be doing a lot in this class is trying to depict the field, right, on a piece of paper or maybe on a computer visualization, a computer model. So the drawing, the actual drawing of field lines and force vectors, or even field vectors, we'll just call it vectors, keep it really general. Okay, that is purely mathematical. It's a tool, okay? So there are no lines in space, okay? It's not like the magnetic field is only existing on particular lines that are traveling through space. The field is continuous and everywhere. Okay, just like a fluid. Okay, so right now, just think you're surrounded by electromagnetic fields, which is something that we didn't really understand to be a real object until Michael Faraday came up with this concept of fields to describe them, and then Maxwell came and actually came up with the mathematics to be able to write down and further understand these fields.